Okay, guys, it's top of the hour. Questions?
As for our data table for lab that's due this week, if we have missing information such as melting points, can we come in and do it before Friday? Get that missing info, or should we just turn in and complete just what we have so far?
Or you just turn in what you have so far.
Okay.
No, can't come in. Everything is, you got 8 weeks to complete everything. Okay. Yes, you turn that in when you come to lab today. Basically, you need to start thinking about the final report. And so, just to nudge you along and to get you doing some things, I ask you for some of the data you have. Okay, guys, let's get started. Any questions about lab this week or anything else?
Are we able to come in for like 5 minutes and stir on our station?
Right after class if you want.
Okay.
Can you?
Actually, yeah. That's fine.
Okay. Or you can stop by any other time, but right after class would be good since you can do it all at once. If you want to stir your air oxidation reaction a little bit, just swirl it around so you can get some mixing. Chemistry of amides. Amides can be hydrolyzed back to the carboxylic acid. Amides tend to be end products. You're not going to convert an amide to an ester. You're not going to convert an amide to an acid chloride. But you can convert amides to carboxylic acids, and then you can convert the acid to anything else. But hydrolysis of amides, either under aqueous conditions, aqueous acid, or aqueous base. You good with those mechanisms there? How do we do with those mechanisms? Good? Okay, hydrolysis of lactams, lactam cyclic amide. I have a product for this here. Let's see, we got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and amine. Yeah. This carboxylic acid. The leaving group has really not left. The nitrogen is still connected to the molecule, right? This is acidic conditions. How's this going to exist?
It's ammonia.
This is going to be protonated here. This is going to be NH3+. Because if you knit a sweater in the pool, it's going to be wet when you get done. You're going to have to dry it. If we hydrolyze the amide under the lactam under acidic conditions, the amine is going to be wet. It's going to be protonated. It can be kind of tough to get this exactly neutral. If you add too much base, you'll deprotonate that, but you can also deprotonate that. So you really going to have to get the pH right to get them both neutral. You can get it both neutral by having maybe the anion. Then it's a net neutral molecule. It could exist maybe as the Zwitter ion. Or you might just show it neutral on both ends. Right? Basically, instead of nitrogen bonding to the carbonyl, we're going to have the OH bonding to the carbonyl. Instead of nitrogen bonding to carbonyl, we've got the OH bonding to carbonyl, and then it may be deprotonated. And the nitrogen has left. Again, it's the same old mechanism. If you haven't sat down and gone through the mechanism and looked at the details and take care of the proton transfer, then you've not done what you need to do. Lactams. Penicillins have the beta-lactam. Called beta-lactams because the first carbon coming off is the alpha, the next one is beta, and the nitrogen is on the beta carbon. By the way, this molecule here, that's an amino acid, but it's not an alpha amino acid. The amine is not on the alpha or the beta. I don't know where that is. It's way out there, but that molecule, that amino acid can be polymerized to give nylon. And there's either something in the handout or in the workbook that mentions that polymerization to give nylon. Yes?
Would it be the omega position? I know you were saying something about that.
Perhaps omega, yeah. That really doesn't tell you how long the chain is. It just tells you it's at the end. Okay, acidity, amides and imides. Acidity, amines, this H really doesn't have much acidity, pKa of about 30. Amides, the H has a pKa more acidic of about 18 to 20. Why is it more acidic?
Carbonyl.
Obviously the carbonyl, that's the difference. Why the carbonyl?
Nitrogen's going into it.
The nitrogen anion, because we want to consider the conjugate base. The nitrogen anion will be stabilized by resonance into the carbonyl, right? Nitrogen bonded to two carbonyls is called an imide. Not an amide, but an imide. And imides are even more acidic because the nitrogen anion, if we consider the conjugate base, we can draw two different resonance structures. We can draw charge localized into one oxygen and then into the other oxygen. Resonance structures, hopefully you see that. Right? Electrons in, electrons up, charge on oxygen. Okay? Now this is a pretty low pKa for a NH. We can do chemistry here very easily. And this is the starting point for the Gabriel synthesis. The Gabriel synthesis of what? Primary amines. In Organic 1, and you can pull that handout out if you had me, we discussed that direct alkylation of amines is difficult. I believe in Organic 1 we saw azides as an alternative. This is a very good alternative route, indirect route for making primary amines. This involves taking this imide called phthalimide, the most common. You can theoretically use a variety of imides, but phthalimide is most common. Treat this with a hydroxide, such as KOH. We'll remove the proton, and we'll be left with the potassium salt of phthalimide, plus water. All right, this is N minus K plus, right? It's just shown as Kn. It doesn't have to be shown with charges, just like if I showed KCl, we know that that's K plus and Cl minus. Well, I can also show Kn. Of course, the nitrogen has to have something bonded to it, so we can show something like this, but it's still K plus N minus, K plus Cl minus. So it's just a way to show that, but that is ionic. Or we can just get rid of the potassium and show the anion. It's the anion that we made here. I just showed the potassium sitting with it. Well, this anion can act as a good nucleophile for SN2. And these electrons can attack the carbon and kick off the leaving group, SN2. And now the nitrogen is bonded to the R group, or the carbon group. Good old-fashioned SN2. Anybody remember what the problem was in organic 1, maybe trying to react ammonia? Here? Polyalkylation. I'll pull that handout back out. It's difficult to react directly with amines, ammonia, or other amines, polyalkylation. You're not going to get polyalkylation with this because this product here will not react again. The lone pair is conjugated. It's not an anion. It will not react again. Game over. We just alkylate once. But now if we come in here and hydrolyze the N-carbonyl, we have to hydrolyze twice. And we can deacylate the nitrogen. Didn't we say deacylation last time on Friday?
Yes.
When you hydrolyze amides, you deacylate them. Right? Over here, nitrogen bonded to carbonyl. No longer bonded to carbonyl. It's been deacylated by the hydrolysis reaction. Instead, the OH is now acylated because we're doing NAS. Every mechanism we've done in the past 2 weeks has been NAS. Under my hand is nitrogen. We do a acyl substitution with water, which is essentially OH. And now under my hand is OH. I've just turned it around, but now under my hand is OH. And it's in the anion form because we're under basic conditions. But the nitrogen has been deacylated. Well, over here we can deacylate this nitrogen, but we just need to do it twice. We need to hydrolyze that bond, and then we need to hydrolyze that bond. Instead of nitrogen bonded to this carbonyl, we're going to have OH bonded to that carbonyl. Instead of nitrogen bonded to that carbonyl, we're going to have OH bonded to that carbonyl, and we're going to make this product. That's called phthalic acid. This is the imide of phthalic acid. That's why it's called phthalimide. Here's our product. Well, and actually in this case, that's not what we want. It's the amine, the deacylated nitrogen. And it becomes a primary amine. And you should see this, and if you don't, you should work through it and see it. And in this case, maybe this is the main product we want. And this we purify out. That can be purified out real easily. How would you do that?
Base titration.
Basically, extraction or washing. Wash it out with base. Treat this with base, it's going to become dianion. That'll be very water soluble, and you can just wash it out into the water, where your amine can maybe be extracted into ether or dichloromethane or something. And you can easily wash out the phthalic acid by washing with base.
We use one of its conjugate bases a lot in quantitative analysis, KHT.
It's the monopotassium salt of, yes? One of these is potassium. One of these is the potassium Ni, and the other is the H there. It's called KHP. It's very often used in quant, yeah?
Yes, sir.
You use it for what?
Just titrations.
Uh,
Base titrations.
what titration?
Base titrations. So like, KOH or,
When you want to determine the concentration of your base,
yes.
okay? The reason being, why do you use KHP? Why don't you use sulfuric acid or something? Why KHP?
It's because it has a carboxylic acid that gets deprotonated and it turns into an anion and then.
Well, why not acetic acid? That has one carboxylic acid. Why not tosyl acid? Why
It's,
not?
works well with, you can use indicators, obviously. And then
You can use an indicator with acetic acid.
I mean, I don't know why we use KHB specifically. It's probably because it's less hazardous or it's not.
Well, that's a good question. Why?
It's
a three-letter
dry,
word.
too.
Why? Great question to ask is why. I think the answer is because you can dry it very well, and when you weigh it out, it's very dry and you get a precise weight on it, where many other acids are wet, and you don't know how wet they are. You can't dry sulfuric acid. When you use sulfuric acid, we really don't know. We know it's 3 molar. We don't know it's 3.089 molar. We can't get that precise. I think the reason why with KHP is you can dry it very well. It's solid, thus it's easy to weigh. It's acidic, but the fact that it's got ionic portion helps it dissolve very easily. So there's a couple of practical reasons why I think it's used. Okay. Yes, KHP. So, in the end, we can get out of this a primary amine in a very good yield. It's a very nice synthesis of primary amines, starting with what? The nitrogen is starting in the imide form. You alkylate it, then you do a double hydrolysis to liberate the amine. Okay? You're only going to get a primary amine here because you're only going to be able to put one R group on. Okay? Called the Gabriel synthesis. During test 4, we'll see another synthesis of primary, well, it could be any. This one's limited to primary. The one we'll see during test 4 is even more versatile. You can make any amines indirectly. So here's a nice line reaction you can show. Predict product there. We'll look at it next time. What can you do with amides other than hydrolyze them back? You can do a specialized Gabriel synthesis. You can convert primary amides to nitriles. Tom? I put this on a handout so we can sort of move through this a little quickly. You pick up the pace a little bit. Okay. Amides, primary amides only can be converted to nitriles. What do we have to remove from the amide to get to the nitrile, to the cyano group?
Hydrogen.
Water. Yes, hydrogen, but not as H2. practically what do we have to remove? We have to remove water, H2O. That's a dehydration. Okay? If we dehydrate a primary amide, we can get the nitrile. Now usually you have to do this, you can't just sort of heat it and dehydrate it, remove, and water is eliminated. Some type of chemical dehydrating reagent. And thionyl chloride will do this. We've used this a couple of times before. We're going to end up with SO2 and HCl. On the yellow sheet, I show that mechanism. You remember the key resonance structure of an amide? Yeah? This resonance structure, I showed you an NMR of DMF. Nothing was not equivalent. Yeah. We said that this is a very important resonance structure for amides. Lots of minus on the oxygen. And indeed, the oxygen is what reacts with the thionyl chloride. Okay, electrons up here, right? We would never just kick off the chlorine. So addition, electrons up, back down. Now we can kick off on the chlorines. We can get to this point here. Chlorine that got kicked off can come in and take an H, these electrons here. At this point, anytime you can make a pi bond using a lone pair, anytime you can make a pi bond and kick off a leaving group, that's easy to do. Is this oxygen a decent leaving group? Well, it's resonance stabilized. We can show resonance. It's somewhat like a tosylate. Okay? But when this comes in and kicks that off, that leads to this. And that's really the cyano group. It's just protonated. Well, this leaving group, it's going to collapse. Anytime you make a pi bond and kick off a leaving group, that's easy to do. So that's going to lead to SO2. Kick off the Cl minus. The Cl minus can take that H. And there we go. We're home. There's your cyano group, and we made both SO2 and HCl. Isn't that nice? See, everything falls into place there? I would expect you could almost do that on your own without even me showing you how. It's very basic, standard chess moves that we've seen up to this point, right? Anything really new there? This crazy new? Okay. Well, indeed, if you go to lab and take a primary amide and heat it with thionyl chloride and then work it up to extract or something, you're going to have the cyano, the nitrile, known chemistry. Just got to make sure you have a good hood because you don't want to be breathing SO2 as it comes out or HCl because they're both gases, and if you're heating this, they're going to be coming out. Okay. You can also do this with acetic anhydride. All right. Basically, we're removing water. But we don't form water. That's just sort of formally, we're dehydrating, removing water to make the nitrile. It is a common way to make nitriles, although not as common as more of the straightforward way of maybe having something like this and treating this with what? Some type of cyanide source. Right? And that would be a good old just SN2, because cyanide can be used as a nucleophile. And that's probably the more common way to make nitriles, is using cyanide to SN2. But dehydration of a primary amide is another way. By the way, I heard about it. I didn't get to it, but apparently Casey and the Sunshine Band was here on Friday night. Yeah, I saw that yesterday. That's why I like Casey and Chemistry of nitriles. Chemistry of nitriles. See it all there? Yeah, there it is. Oh, that was quick, wasn't it? What can you do with nitriles? Well, you can synthesize them, and we just showed 2 ways to do that. Nitriles also tend to be end products. Although, for me, no, not really. They can be used a number of things. They can be, there's some chemistry that we won't be talking about, so I can't just say end products. I'll show you a couple of here. I almost showed you this a while back. If you can see this. This is a compound with a furan, a benzene ring, and a nitro group. Now the benzene ring and the nitro is on both sides of the furan. Remember furan, aromatic we talked about? It's on both sides. I didn't draw it on both sides. I just showed the squiggly line. It's over there also. The furan is symmetrical. That's the nitro group. Here's the analogous compound with the cyano groups. And both the nitro and the cyano here are sort of, well, these are important compounds to me and past work I've done. It's actually the cyano compound was made by a student here a while back. I think I made the nitro compound. I'll pass these around if you want to take a look. The nitro is orange. You may have seen a little orange before, although the nitrofluorine is really not supposed to be orange. It's more of a tannish yellow. But this nitro, it's a dinitro, orange. But also the cyano group, and the cyano groups can be converted to other things, but we won't be talking about that here. The main thing we'll be doing here is looking at the hydrolysis. The nitrile group is an acid derivative. Why is it an acid derivative? There's no carbonyl. Why is it an acid derivative? Hopefully this was clearly explained in the nomenclature video. Why is it an acid derivative?
It's bonded to, it has 3 bonds to a more electronegative.
3 bonds to a more electronegative atom, just like a carboxylic acid. So it's at the same oxidation state as a carboxylic acid. And any acid derivative, and there are other ones that we aren't showing here, but guess what? Any acid derivative can be hydrolyzed back to a carboxylic acid. All right? And it does not require redox because they're at the same oxidation state. A cyano group can be hydrolyzed to the carboxylic acid. How would we do that? Under acidic conditions, we can do it. What would you do first under acidic conditions? Protonate something. What would you protonate?
The nitrogen.
The nitrogen of the nitrile. This makes the carbon more electrophilic because the nitrogen is now pulling even more. More partial positive here. Analogous to the same thing like with the carbonyl. Protonate carbonyl or protonate nitrile. Now water will add to the carbon, electrons over. Get to this point. What are we trying to accomplish? First thing, when you hydrolyze to an acid, you go through the amide. Because what do you get if you add water to a nitrile? Primary amide. What do you get if you remove water from a primary amide? Nitrile. We just did that previously. So we're doing the opposite. We're adding water to the nitrile. That gives an amide. And when you add water, it's called a hydrolysis. Okay? So we're going to get the amide back first. We want 2 H's on nitrogen. Get here. How about a proton transfer? Sort of basic. We can move the acidic proton here. Yeah? Now we can do resonance. Electrons here, electrons here. Get this. And now something, you take the H, I shouldn't be doing that. Not good, not good. I used to allow this, but I had to put an end to it. This needs to be a full structure. Right? These electrons take the H. And what does that give? That gives us our amide. And what do? We reform H2SO4. Right? And so we added water to the nitrile using an acid catalyst. We reformed our catalyst. Acid catalyzed hydrolysis. All right? To the amide. But guess what? Amides can be hydrolyzed to the acid. So you just hydrolyze further. And we've already done that. That was done on previous pages. Now, maybe he expected you to show that mechanism yourself. But if you kept on going, what would be the first step?
Protonate carbonyl.
Protonate the carbonyl, then what's next? Water adding to carbonyl. Oxygen nucleophile, electrons up.
And then electrons back down, kick off.
I think it'd be a proton transfer first.
And then
Make nitrogen a better leaving group. Okay. Overall, it's nucleophilic acyl substitution, which is an addition and an elimination. But you got to take care of the proton along the way at some point and at the appropriate point. Okay. Eventually those electrons will come back down and kick off the nitrogen. Ultimately, you're going to form ammonia, but under acidic conditions, the ammonia will exist as ammonium, NH4+. You should do that mechanism on your own. So it's really a double hydrolysis. First hydrolysis gets you the amide, and then you hydrolyze again to get back to the carboxylic acid. So that can all be done in one reaction, where this is not isolated. Brackets mean it's not isolated. Sometimes it can be. Sometimes if you do this exactly right, you can get the amide, which sort of implies to me that this may be easier than that. But for us, sort of all the way here, double hydrolysis to the carboxylic acid. Now you can also do this under basic conditions. Under basic conditions, what's the first step?
hydroxide attacks the carbon.
Yeah. And also this is just showing sodium hydroxide, and maybe I do that as well. But you're also, it's going to be aqueous, and so there also needs to be water, and actually that hydroxide is catalyst. So above it is water and acid, below it's water and base. And here, we can't protonate the nitrile, so it's less reactive. And water actually does not react with nitrile, but hydroxide will. Again, there's no proton. We're not under acidic conditions. Only going to protonate something under acidic conditions. Nucleophilic addition to the cyano group would give this. We generate an anion here. We need H's on the nitrogen. Where can we get an H from? Water can serve as a proton source. Here's a common mistake I see here often. I see protonation of nitrile, and then I have to say, how? How did you do that? We don't have a proton. There's no strong acid here. Next mistake I see somebody will just draw an H plus here, and this is going to attack there. There's no H plus. The proton source here is water. That's going to give you the H on the nitrogen, and it will generate hydroxide. Right there, we regenerate hydroxide, right? We need to get rid of H's on oxygen. They're gone. This can take an H from there. Get the anion again. Then we can do resonance. Now we're looking like amide, right? This just needs an H. Where can they get an H from? Water. Because we form water back over there. And ultimately, when this takes an H, we get our amide. And what do we regenerate right here?
Catalyst.
Hydroxide reformed. Everything falls into place. Okay? And ultimately, we consume one equivalent, 1 mole of water. Okay? Because we've added water to the nitrile, using hydroxide as as catalyst. Basic catalyst. I could have just said proton transfer here. Anytime you do proton transfer, it's likely that something takes it and then that the other thing takes it right back. And that's sort of what I did. Hydroxide takes it. Well, then the nitrogen, I'm sorry, not hydroxide, nitrogen takes it, and then the hydroxide takes it right back. It seems flipped there, but ultimately we could have just said proton transfer. Instead of the proton going to hydroxide and then coming back or it being taken back, we could have just transferred. So that is possible, and we've done that before. One key thing, look at the mechanisms at top and below. Charges. In the mechanism we just did, every intermediate has what type of charge? Either anion, or neutral. How about the one above? What were the charges up there? Positive or neutral. Very important to recognize this. I could have pointed this out before. If you're under acidic conditions, your intermediates are always going to be positively charged. If you're under basic conditions, your mechanistic intermediates are always going to be negatively charged. Or neutral. Okay? That's sort of a theme to recognize with your mechanisms. Okay, well, of course, the primary amide can be hydrolyzed further. Let's call this aqueous to the carboxylic acid. Of course, the acid is going to be in the anion form if you do this reaction under basic conditions, right? Chemistry of nitriles. And that's largely acid derivative chemistry that we're covering. Miscellaneous topics here. You know this molecule here? Carbonic acid. Kind of looks like a double carboxylic acid. All right? Well, it's not a carboxylic acid. It's not a carboxylic acid derivative. But I want to kind of discuss this a little bit. It's very common. It's called carbonic acid. It's actually not stable, because carbonic acid will break down into what? H2O plus CO2. It will decompose to give these two molecules. You may have made a volcano in 3rd grade. How do you make a volcano? You put in
Baking soda.
baking soda, which is sodium bicarbonate, and then you add an acid. When you add an acid, you get an acid-base reaction and you generate carbonic acid. But carbonic acid, as soon as it's formed, turns into what?
CO2 and water.
CO2 and water. The CO2 comes out and it causes bubbling and stuff. Okay? Because CO2 is a gas. Now this is theoretically a nice equilibrium. I mean, you can come back this way. But if you do this open and the CO2 escapes, what's going to happen to this equilibrium? It's all going that way. And ultimately, as the CO2 escapes, everything is just gone. You'll just be left with water. Because the equilibrium is driven by the escape of the CO2. If you did this in a balloon or something, or you could actually drive it this way, how would you drive it that way?
Use the CO2 trap.
Lots of CO2. Okay? Why is your Coca-Cola acidic?
Lots of CO2.
Because it has lots of CO2 in it, under pressure. CO2 and water under pressure generates what? Carbonic acid. It's acidic. Okay? CO2 is thus a what? It's an Arrhenius acid, right? Is that the right definition of Arrhenius acid? What's the definition of Arrhenius acid? Donald? Definition of Arrhenius acid. This is it's 8th grade for me, I think. Arrhenius acid generates H plus when put in water. What does CO2 generate when you put it in water?
H plus.
H plus. Carbonic acid, an acid is H plus. Yes. CO2 is an acid. Did you know CO2 is an acid? Well, it's an Arrhenius acid. It's not a Bronsted-Lowry acid. Bronsted-Lowry acid has to have an H. But Arrhenius acid does not. CO2. Because way back then, all they knew is you put CO2 in water, you had acid. So they said CO2 is an acid. So they gave me acid. All right? Yeah. But you might have to put some pressure on it. Or a little bit. You put CO2 in, you'll get a little bit. It'll be like 99, you'll get 0.1 of this. But as the CO2 escapes, this goes back the other way. Okay. That's free review of Gen Chem. What type of derivatives can you have of carbonic acid? Well, first off, this is not stable either. Not stable. This is going to just lose CO2 because this basically, electrons come the other way. These electrons move here and this gets kicked off. But this picks up a proton, you're going to make CO2 here. What is stable here? The diesters are stable. The diacid's not. The diester is stable. It's called diethyl carbonate. The dichloride is actually stable. That's called phosgene. Okay? Actually very reactive. You think this acid chloride is reactive with 1 chlorine. What about 2? Very reactive. Very toxic reactive gas. It was used as a chemical war gas in World War I. The diamide is actually stable. Stable molecule. You might know the name of this molecule. It's got a very common name. What is this?
Diamide.
That's right. That's urea. Everybody know that, right?
Mm-hmm.
Yeah.
Urea. Mixed derivatives are stable. See, basically, that's a carbonic acid derivative. These are all. But here, these are important to know, though. The monosodium salt of carbonic acid is stable. What is that?
Bicarbonate.
That's sodium bicarbonate. And this is baking soda. And if you treat it with acid, you're going to protonate that O minus. And if you protonate that O minus, what do you get?
CO2.
Carbonic acid. And carbonic acid is not stable and it decomposes. So that's how this leads to CO2. Now you can also have the double sodium salt or potassium. What's that called? It's not sodium bicarbonate, but just
Sodium carbonate.
sodium carbonate, or potassium carbonate, or a variety of others. Okay? That's bicarbonate, and that's just carbonate. Both of those types of salts are stable. But you treat these with acid, you're going to make carbonic acid, and it's going to decompose. There's nylon 6. These are polymers. If you consider this molecule here, this nitrogen can come in here and just substitute the OH. But if it did it intramolecularly, we'd get the amide. And we can lose water. And that's going to require some type of activation because ultimately this is probably going to be existing like this, and this is not going to lose water, not be electrophilic. So it's going to require some type of activation. But imagine instead of this amine attacking this carbonyl, what if it attacked the carbonyl of another molecule? Well, then you would have it bonded to the carbonyl of another molecule. And then coming off the end of the other molecule would be what?
Another molecule.
An H2, yeah? Well, what if this attacked the carbonyl of another molecule? Then this would be bonded to a carbonyl. And what would be coming at the end of that? An H2. And what if this attacked the carbonyl of another molecule? It would become that. And what would be at the end of that? An H2. And you can go on and on and on. And what am I building here?
Polymer?
I'm building this polymer here where it's nitrogen bonded to carbonyl. Or if we come this way, nitrogen bonded to carbonyl, what's at the end of the carbonyl? In nitrogen, but it can attack the carbonyl of another. And what's at the end of that other molecule? Okay? You see how I built that up? But this is that's nylon 6, or, okay? It's called nylon 6, I think, because it's 1, 2, 3, 4, 5, 6. I don't know why they didn't call it nylon 7. I think it has to do with the number of carbons there, other than the carbonyl. This is called a condensation polymerization. Because for the nitrogen to end up being bonded here, you lose water. You lose the OH here plus one of the H's from the nitrogen. Okay? So it's a condensation polymerization. Whenever you form water, that's called condensing out water. This is a homopolymer. What is a homopolymer?
Single.
A homopolymer is where one molecule self-reacts. It's just, okay, the same. On the other side, there's some other polymers. Basically, the amide polymers are very common. Ever heard of Kevlar? Used to make bulletproof vests. Here's a polymer of Kevlar. It's an amide polymer. What molecules react to give Kevlar? In this case, it's two different molecules. I want you to see if you can show that, and we'll maybe look at that next time. What two molecules can react by a condensation polymerization to give Kevlar? And it's not a homopolymer, it's called a copolymer. It's two different molecules. Okay, and there's some other ones here. You can also have polyesters. Anybody ever heard of polyester? Right? Leisure suits. Polyester leisure suits.
Mm-hmm.
Or polyester rain jackets. Okay. Polyesters, different polyesters. Basically, how would you make these polymers? What's the monomers? What are the starting materials? Is it one monomer or is it two different ones coming together, which would be a copolymer, copolymerization? Please look at that. How would you make those polymers? One of the ultimate, most important polymers is amino acids, polymerizing to give proteins, peptides. Peptides come from amino acids. Hey, that's just like what we did here, right? We've got an amine and an acid. Amine and an acid. If one amine condenses with the carbonyl, then you're going to have an amine on the end. It's the same type of thing, except that's an alpha amino acid. And when that polymerizes, instead of getting nylon, you get something like a peptide. But here, the R group can vary on each linkage, and as the R group varies, that gives you different peptides and different proteins and stuff. So it's a really mixed polymer. If you try to do this in lab, you just get a messy mix. But the body does it very nicely and gives a variety of peptides because the body can control these processes. Okay? And you can get different R groups here, and it's amazing. Right? Okay, guys, have a good day. The other handout will begin on Wednesday after our quiz. It was the other blue one, yeah?
Yeah.